Hello, friend. Welcome back to another journey through the cosmos. Tonight, we're going to explore something so strange, so fundamentally bizarre, that even Albert Einstein himself struggled to accept it when he first discovered it in his own equations. Right now, as you lie in bed listening to this, the space between you and the nearest star is growing. Not because anything is moving, but because space itself is stretching, expanding, creating new distance where none existed before. Every second, thousands of kilometers of new space appear between galaxies. And here's what makes it truly unsettling. Einstein found this in his math in 1917, saw what it meant, and was so disturbed by the implications that he actually changed his equations. He called it the biggest blunder of my life. Oh, but was it really a blunder? Or was the universe trying to tell us something so profound that even the greatest mind of the 20th century couldn't quite believe it? If you're curious about the mysteries hidden in the night sky, mysteries that unfold while the world sleeps, go ahead and hit that like button. And subscribe to join us on these cosmic journeys where science meets storytelling, and where the universe reveals its secrets in the quietest hours of the night. It was the winter of 1917 in the middle of World War I, when Albert Einstein sat alone in his study in Berlin, staring at equations that refused to behave. He had just completed his masterpiece, his general theory of relativity, published the year before. The equations were beautiful, elegant, describing how mass and energy curve the fabric of space-time itself. Gravity wasn't a force pulling objects together, Einstein realized. It was the shape of space itself, warped by the presence of matter. But there was a problem. When Einstein tried to apply his equations to the entire universe to describe the cosmos as a whole, something unexpected emerged. The math insisted that the universe couldn't be static. It had to be either expanding or contracting. Space itself had to be changing, growing, or shrinking over time. This contradicted everything astronomers believed in 1917. The universe was supposed to be eternal and unchanging. The stars had always been where they were and always would be. This was simply how things worked, how they had always worked. Einstein was troubled. His equations were telling him something that seemed impossible. So he did something that haunted him for the rest of his life. He added a term to his equations, a mathematical fudge factor he called the cosmological constant. This constant, represented by the Greek letter lambda, acted like a repulsive force that exactly balanced gravity, holding the universe perfectly still. It was artificial, he knew. It had no physical basis, but it made the universe static again, and that's what the science of the time demanded. For 12 years, Einstein's modified equations stood as the accepted description of the cosmos, a static, eternal universe held in perfect balance by this mysterious cosmological constant. But across the Atlantic Ocean, at the Mount Wilson Observatory in California, an astronomer named Edwin Hubble was making observations that would shatter this peaceful picture forever. Hubble was measuring the light from distant galaxies using the most powerful telescope in the world, at that time, the 100-inch Hooker telescope. Night after night, he captured spectra of light from these cosmic islands of stars, and what he found was astonishing. The light from nearly every galaxy he observed was shifted toward the red end of the spectrum. This redshift, as it came to be called, had a very specific meaning. It meant the galaxies were moving away from us. But here's what made Hubble's discovery truly revolutionary. The farther away a galaxy was, the faster it appeared to be receding. This wasn't random motion. It was a pattern, a relationship that suggested something fundamental about the structure of the universe itself. In 1929, Hubble published his findings, and the astronomical community had to face an uncomfortable truth. The universe was expanding. When Einstein learned of Hubble's discovery, he traveled to California to see the evidence for himself. He looked through the telescope, examined the data, and realized what he had done. His equations had been right all along. The universe was expanding just as the math had predicted, by adding the cosmological constant, by forcing the universe to be static. He had missed the chance to make one of the greatest predictions in the history of science. He could have told astronomers what to look for years before Hubble's observations. Instead, he had second-guessed his own equations. If Hubble's expansion had been discovered at the time of the creation of the general theory of relativity, the cosmological constant would never have been introduced, Einstein later wrote. He called it his biggest blunder, this failure of nerve, this moment, when he had let philosophical prejudice override mathematical truth. But let's pause here and really think about what expansion means, because this is where most people's intuition starts to break down. When we say the universe is expanding, we don't mean that galaxies are flying apart through space like debris from an explosion. That's the common misconception, and it's completely wrong. The galaxies aren't moving through space at all. Space itself is expanding, stretching, creating new distance between objects that remain essentially motionless. Think of it this way. Imagine you have a deflated balloon and you draw dots on its surface to represent galaxies. Now, as you inflate the balloon, what happens to the dots? They move apart from each other, right? But here's the crucial point. No dot is moving across the surface of the balloon. Each dot stays in exactly the same place on the rubber. It's the rubber itself that's stretching, carrying the dots along with it. That's what's happening in our universe. We're not the dots moving through space. We're the dots painted on space as space itself expands. This distinction might seem subtle, but it has profound implications. If galaxies were actually moving through space flying apart from some central explosion, then we could ask, where did the explosion happen? Where's the center of the universe? But if space itself is expanding uniformly in all directions, then there is no center. Every point in space sees every other point moving away from it. The expansion looks the same from anywhere in the universe. Here's something even stranger. If space itself is expanding, then it's not limited by the cosmic speed limit of light. Einstein's relativity says that nothing can move through space faster than light. But space itself isn't moving through anything. It's simply growing, and there's no law of physics that limits how fast it can grow. Right now, there are galaxies receding from us faster than the speed of light because of the expansion of space. We'll never be able to see them, never be able to send signals to them, because the space between us is growing faster than light can cross it. This was the reality that Einstein's equations had tried to tell him in 1917. The universe is not static. It's dynamic, changing, expanding every moment. And this expansion isn't something that happened only in the distant past. It's happening right now, as you listen to this, as you breathe, as you slowly drift towards sleep. Think about it. Since you started listening to this story about Einstein's sleepless night, the universe has grown. New space has been created. The distance between our Milky Way galaxy and the Andromeda galaxy, about 2.5 million light-years away, has increased by thousands of kilometers. You didn't feel it. You never will feel it. But it happened. The expansion of space is so fundamental to our cosmos that it's built into the very structure of reality. It's been happening for 13.8 billion years, since the moment we call the Big Bang, though. That's a misleading name. There was no bang, no explosion in space. There was the sudden expansion of space itself from an infinitely dense state into the vast cosmos we inhabit today. And that expansion has never stopped. Einstein eventually came to embrace the expanding universe. He visited Hubble at Mount Wilson multiple times. He revised his equations, removing the cosmological constant. He even wrote papers exploring the implications of cosmic expansion. But he never quite forgave himself for that moment of doubt, that failure to trust his own mathematics. Yet, here's the beautiful irony that Einstein didn't live to see. In 1998, astronomers made another shocking discovery. Not only is the universe expanding, but the expansion is accelerating, getting faster over time. And the best explanation we have for this acceleration is something that looks very much like Einstein's cosmological constant, that blunder he regretted so deeply. It turns out that empty space itself has energy, a kind of pressure that pushes the universe apart. We call it dark energy, and it behaves exactly like Einstein's constant. So, Perhaps it wasn't a blunder after all. Perhaps Einstein's intuition was right, even when he thought he was wrong. The cosmological constant was real. He just had the sign wrong, and he gave up on it too soon. What kept Einstein awake that winter night in 1917 wasn't just mathematics. It was the vertigo of standing at the edge of a profound truth about reality. The universe isn't a fixed stage where events play out. The stage itself is changing, growing, evolving. We live in a cosmos where space itself is alive, in a sense expanding and stretching, carrying galaxies along, like leaves on a flowing river. And this expansion connects to something deeply human, something that perhaps resonated with Einstein on an intuitive level. Nothing lasts forever. Everything changes. Even the distances between stars, even the fabric of space itself, is subject to time's arrow. The universe is not eternal and unchanging. It had a beginning, and it will have an end transformed by this relentless expansion into something cold and dark and unimaginably vast. But for now, for this brief cosmic moment, we exist in an era when stars still shine, when galaxies cluster together, despite the expansion, when matter and energy are still concentrated enough for life to emerge and contemplate its own existence. We are here in the universe's youth, relatively speaking, asking the same questions that kept Einstein awake. What is space? Why does it expand? Where is it all going? These questions might seem abstract, disconnected from our daily lives, but they're not. Understanding that space itself is expanding changes how we think about our place in the cosmos. We're not just living in space. We're living in a dynamic, evolving space that's been carrying us along on a 13.8 billion year journey from an infinitely hot, dense beginning toward a cold, empty, infinitely expanded future. So, tonight, as you close your eyes, as your breathing slows and sleep begins to find, you remember Einstein in his study, staring at equations that told him the universe was alive with motion. Remember that the cosmos is not a static backdrop, but a dynamic arena, constantly changing, constantly growing. And somewhere in that thought, in that connection between the human mind and the mathematical structure of reality, there's something almost magical. We are the universe trying to understand itself, and we're doing it while the very stage beneath us expands into the infinite dark. But understanding that space expands is just the beginning. The really fascinating question is, how did we figure this out? How do you measure something as abstract as the stretching of space itself? The answer lies in light in the colors of distant galaxies and in a discovery made even before Einstein's equations. It's a story of whispers from across the cosmos, messages written in wavelengths of light, telling us that everything is moving away. Let's follow that thread and see where it leads. Imagine you're holding a photograph of your childhood home. Now imagine that while you're looking at it, the photograph itself starts growing, stretching in all directions. The house gets bigger, the yard expands, but nothing in the picture is actually moving. That's not how photographs work, of course. But that's exactly how the universe works. And the reason we know this, the reason we can confidently say that space itself is expanding rather than objects simply flying apart, comes down to one of the most elegant demonstrations in all of cosmology. It's called the balloon analogy, and while you've probably heard of it, what most people don't realize is just how precisely it maps onto reality and, more importantly, where the analogy breaks down in ways that reveal even stranger truths. If this cosmic mystery intrigues you, if you want to understand the difference between moving through space and space itself, expanding, go ahead and give this video a like. And subscribe so you don't miss the rest of this journey through the expanding cosmos where we unravel the science that unfolds while you sleep. Let's go back to 1931 to a Belgian priest and physicist named Georges Lemaitre. Most people remember Einstein and Hubble when they think about cosmic expansion, but Lemaitre was the one who truly understood what it meant. He was the first to propose what he called the primeval atom, the idea that the universe began as an infinitely dense point and has been expanding ever since. We now call this the Big Bang, though Lemaitre himself disliked that term. It was actually coined as an insult by astronomer Fred Hoyle, who thought the whole idea was ridiculous. Lemaitre needed a way to help people visualize expansion without falling into the trap of thinking about galaxies flying through space. So, he proposed a thought experiment that has become one of the most famous analogies in science. Picture the surface of a balloon, he suggested. Not the three-dimensional volume of the balloon, but just the two-dimensional surface. Now, imagine painting dots on this surface to represent galaxies. As you inflate the balloon, what happens? Every dot moves away from every other dot. But here's the crucial insight from the perspective of an ant living on the surface of the balloon, who can only perceive the two-dimensional surface and has no concept of the three-dimensional space the balloon occupies. There is no center to the expansion. No matter which dot the ant stands on, it sees all the other dots moving away. And the farther away a dot is, the faster it appears to recede. This is exactly what Hubble observed in 1929. It's what we still observe today. But let's dig deeper into why this matters, because the distinction between expansion and explosion is not just semantic. It reveals something fundamental about the nature of space itself. When something explodes like a firework or a bomb, matter moves outward from a central point through pre-existing space. There's a clear center to the explosion. If you could rewind time, you could trace all the debris back to the exact point where the explosion occurred. And here's the key. The debris is hottest and fastest at the center, and cooler and slower at the edges. The universe doesn't work like this at all. When we look out into space in every direction, we see the same thing: galaxies receding from us in proportion to their distance. There is no center, or rather, everywhere is the center. This only makes sense if space itself is expanding uniformly, carrying the galaxies along with it, like currents carrying boats on an ocean. Here's where it gets really interesting. If galaxies were simply flying apart from some cosmic explosion 13.8 billion years ago, we could calculate their trajectories and figure out where the center of that explosion must be. Astronomers have tried this. They have mapped the motion of thousands of galaxies in every direction. And the result? There is no center. The expansion is isotropic, meaning it looks the same in all directions from every vantage point. This is only possible if space itself is what's expanding. Think about what this means for your place in the cosmos. You are not fleeing from some cosmic ground zero. You're not on the edge of anything or in the middle of anything. You're simply here in a space that's stretching uniformly in all directions. Every galaxy could claim to be at the center of the expansion, and every galaxy would be equally correct. This is the cosmological principle on large scales. The universe looks basically the same from anywhere. Now, let's address the most common misconception about the balloon analogy, because this is where most explanations go wrong, and where your understanding needs to be precise. When people picture the balloon, they naturally think about the three-dimensional space inside and outside the balloon. They imagine the dots moving outward into the space inside the balloon, or away from its center. But this is exactly what you should not imagine. The correct version of the analogy requires you to think only about the two-dimensional surface. The interior of the balloon doesn't represent anything physical in our universe. It's just a mathematical dimension that helps us visualize what's happening. Our universe is the surface of the balloon, not the volume. And just as the surface has no center, no edge, and no inside or outside that's accessible to creatures living on the surface, our three-dimensional space has no center, no edge, and possibly no fourth spatial dimension that we can access. We are trapped in our dimensional slice of reality, just as the ant is trapped on the balloon's surface. But here's where the analogy breaks down in a fascinating way. A real balloon expands into the air around it. That air is a pre-existing three-dimensional space. So, when people ask, what is the universe expanding into? They're imagining something like the air around the balloon. But the universe isn't expanding into anything. There is no pre-existing space outside the universe waiting to be filled. Space itself is being created by the expansion. This is one of the hardest concepts in cosmology to grasp because it contradicts every intuition we have about how things grow or move. Let me give you a different analogy that might help. Imagine you're a character in a video game living in a simulated world. The game world is, let's say, 100 kilometers wide. Now, imagine the programmer decides to expand the game world to 200 kilometers wide. From your perspective as a character in the game, new terrain suddenly exists. The distance between cities is doubled. But the game world didn't expand into anything. The programmer didn't create new memory storage space outside the original game. They simply redefined the parameters of the simulation. More world now exists, but it's not existing in some external space. It's just more world, period. That's closer to what's happening with cosmic expansion. The universe isn't growing into some pre-existing void. The very concept of void or space only exists within the universe. Outside the universe, there isn't even nothing. There's no outside at all. The question, what is the universe expanding into, is like asking, what's north of the North Pole? The question contains a category error. It assumes there must be something beyond when the very framework that would make that something possible doesn't exist. Now let's talk about the speed of expansion, because this is where the balloon analogy becomes quantitatively useful. Remember how I said that the farther away a dot is on the balloon, the faster it recedes. This is called Hubble's law, and it's one of the most precisely measured relationships in all of astronomy. The current best estimate is that space expands at about 70 kilometers per second per megaparsec. A megaparsec is about 3.26 million light years. So, for every 3.26 million light years of distance between you and a galaxy, that galaxy appears to recede at an additional 70 kilometers per second. Let's make this concrete. The Andromeda galaxy is about 2.5 million light years away, which is roughly 0.77 megaparsecs. By Hubble's law, it should be receding from us at about 54 kilometers per second due to cosmic expansion. But here's the interesting thing. Andromeda is actually moving toward us at about 110 kilometers per second. Why? Because the local gravitational attraction between the Milky Way and Andromeda is stronger than the expansion of space trying to pull us apart. Gravity wins on these small scales. We'll talk more about why that is later, but for now, just note that expansion is only dominant over very large distances. The Virgo cluster. A massive collection of galaxies about 65 million light-years away is receding at about 1,200 kilometers per second. The Coma cluster, 320 million light-years away, recedes at about 7,000 kilometers per second. And here's where it gets wild. The most distant galaxies we can observe, nearly 13 billion light-years away, are receding at speeds approaching the speed of light itself, about 300,000 kilometers per second. And beyond a certain distance, galaxies are receding faster than light. We'll never see them, never know they're there, because the space between us is growing too fast for their light to ever reach us. This brings us to another crucial difference between expansion and explosion. In an explosion, objects have different speeds based on how much energy they receive from the explosion. Some pieces fly fast, some slow, but each piece has a fixed velocity through space. In cosmic expansion, no galaxy has a fixed velocity. A galaxy that's receding from us at, say, half the speed of light isn't moving through space at that speed. The space between us and that galaxy is growing, and the growth rate is proportional to the distance. If the universe's expansion rate suddenly doubled, every galaxy would appear to recede twice as fast, but no galaxy would have accelerated in the traditional sense. Here's a thought experiment to illustrate this. Imagine you and a friend are standing 1 meter apart on the surface of our balloon. Space is expanding at a rate such that every meter grows by 1 centimeter per second. So you and your friend are separating at 1 centimeter per second. Now imagine another person standing 2 meters away from you. They're separating from you at 2 centimeters per second, even though they're not moving any faster across the balloon's surface. They're just farther away, so more space is being created between you and them. Someone 10 meters away separates at 10 centimeters per second. Someone 1,000 meters away separates at 10 meters per second. And if someone is far enough away, the space between you and them is growing faster than you could ever travel across the balloon's surface, even at the maximum speed allowed by the balloon's physics. That's our universe. That's why there are galaxies we will never reach, never contact, never see. Not because they're moving faster than light through space, but because space itself is creating new distance between us, faster than light can cross it. The expansion of space doesn't violate relativity's speed limit because nothing is actually moving through space. Space itself is growing. Can you feel how different this is from an explosion? In an explosion, if you were fast enough, you could always catch up to the debris. The debris has a fixed speed, and if you go faster, you can reach it. But in an expanding universe, the farther away something is, the faster the space between you grows. There's a horizon beyond which catching up becomes impossible, no matter how fast you travel. This horizon, called the Hubble sphere, is currently about 14 billion light-years away. Everything beyond that is receding faster than light, unreachable forever, even if we could somehow travel at light speed ourselves. Let's return once more to Georges Lemaitre because his insight went even deeper than the balloon analogy suggests. If space is expanding now, he reasoned then, it must have been smaller in the past. Wind the clock back far enough, and all of space would have been compressed into an infinitely small point. This was the primeval atom. He proposed the origin of everything. Not an explosion in space, but the explosive expansion of space itself, from a state of infinite density. When Lemaitre first proposed this idea at a conference in 1927, Einstein was in the audience. Einstein stood up and said, "Your calculations are correct, but your physics is abominable." He couldn't accept it. A universe with a beginning, a universe that changed over time, violated everything Einstein believed about cosmic eternity. But 2 years later, Hubble published his observations of galactic recession, and Einstein had to admit that Lemaitre was right. Space was expanding, and it had been expanding from some initial state. The balloon analogy helped people visualize this, but it also created a new problem. If the universe began as an infinitely small point, and it's been expanding ever since then, what's outside the balloon? What was there before the expansion began? These questions still haunt cosmology today, and we don't have complete answers. But the analogy at least helps us see why the questions themselves might be flawed. The balloon's surface is all there is. There is no outside. Similarly, the universe might be all there is with no outside and no before. Space and time themselves might have begun with the Big Bang. Think about this as you lie here in the dark. The space around you is the same space that began expanding 13.8 billion years ago. It's older than the atoms in your body, older than the Earth, older than the sun. And it's still growing, still stretching, carrying galaxies along with it like leaves on a vast cosmic current. You can't feel it. You never will. But it's happening, has been happening, will continue happening long after you and I and the sun itself have turned to dust. The balloon taught us how to think about expansion without getting trapped in the explosion metaphor, but it didn't tell us how we know the expansion is real. For that, we need to look at light itself, at how the stretching of space leaves its fingerprints on every photon that crosses the cosmos. We need to understand redshift. There's a secret written in every beam of starlight that reaches Earth, a code embedded in the colors themselves. This code tells us not just where stars and galaxies are, but how fast they're moving away from us, how old they are, and how long their light has been traveling through the expanding universe. The strange thing is, we almost missed this code entirely. It was discovered by accident in 1912, 17 years before Hubble's famous observations, by an astronomer who was simply trying to measure the speed of spiral nebulae. He had no idea he was documenting the expansion of the universe itself. His name was Vesto Slipher, and his story is one of the most overlooked chapters in the history of cosmology. If you're fascinated by how scientists decode messages from across the cosmos, Messages written in wavelengths of light, hit that like button. And subscribe to journey deeper into these cosmic mysteries where the universe speaks to us through colors we can barely see. Let's set the scene. It's 1912 at the Lowell Observatory in Flagstaff, Arizona. Vesto Slifer is a methodical patient astronomer working under Percival Lowell, the wealthy amateur astronomer who was obsessed with finding canals on Mars. While Lowell chased his Martian fantasies, Slifer was doing serious work pointing the observatory's 24-inch telescope at fuzzy patches of light called spiral nebulae. No one knew what these objects were yet. Some astronomers thought they were nearby clouds of gas within our own Milky Way, possibly forming new solar systems. Others suspected they might be something far more distant and profound. Slifer's goal was to measure their rotation speeds using a technique called spectroscopy. When you pass starlight through a prism or diffraction grating, it spreads into a rainbow of colors called a spectrum. Within this spectrum are dark lines, absorption lines, created when atoms in the star's atmosphere absorb specific wavelengths of light. Every element creates a unique pattern of these lines, like a fingerprint. Hydrogen creates one pattern, helium, another calcium, yet another. By identifying these patterns, astronomers can determine what stars are made of. But Slifer noticed something strange. When he photographed the spectrum of the Andromeda Nebula, the absorption lines weren't quite where they should be. They were shifted slightly toward the blue end of the spectrum. This could only mean one thing: Andromeda was moving toward us. The motion was causing what's called the Doppler effect, the same phenomenon that makes an ambulance siren sound higher pitched as it approaches and lower pitched as it recedes. With light motion toward an observer, compresses wavelengths, shifting light toward the blue. Motion away stretches wavelengths, shifting light toward the red. How much was Andromeda shifted? Slifer calculated that it was approaching us at about 300 kilometers per second, an absolutely staggering speed by early 20th century standards. Nothing on Earth moved anywhere near that fast. Even the Earth's orbit around the Sun is only 30 kilometers per second. Andromeda was hurtling toward us 10 times faster than that. But the real shock came when Slifer turned his telescope to other spiral nebulae. Between 1912 and 1917, he measured the spectra of 25 different nebulae. Of these, 21 showed redshift, meaning they were moving away from us. Only 4, including Andromeda, showed blue shift, and the speeds were enormous. Some nebulae were receding at 1,000 kilometers per second, even 1,800 kilometers per second. These weren't gentle drifts. These were velocities that suggested something fundamental was happening on a cosmic scale. Slifer presented his findings at the American Astronomical Society meeting in 1914. The audience gave him a standing ovation, the only standing ovation ever recorded in the Society's history up to that point. They recognized they were witnessing something profound even if they didn't fully understand what it meant. Were these nebulae being flung away from some ancient explosion? Were they somehow racing through space at these incredible speeds? The data was clear, but its interpretation remained murky. It would take 15 more years and the work of Edwin Hubble to put the pieces together. Hubble's crucial contribution wasn't discovering redshift. Slifer had already done that. Hubble's breakthrough was measuring distances to these nebulae and showing that they weren't nebulae at all. They were galaxies' vast islands of stars far beyond the Milky Way. And here was the key insight: the farther away a galaxy was, the greater its redshift. Distance and recession velocity were proportional. This could only mean one thing: space itself was expanding. But let's dive deeper into what redshift actually is, because understanding this phenomenon is crucial to understanding cosmic expansion. Imagine a wave on the ocean. It has a wavelength the distance from one crest to the next. Now imagine you're stretching the ocean itself while the wave travels across it. As space stretches, the wave stretches with it. Its wavelength gets longer. With light, longer wavelengths mean redder colors. Blue light has a wavelength of about 450 nanometers. Red light has a wavelength of about 650 nanometers. As light travels through expanding space, its wavelength increases, shifting toward the red end of the spectrum. This is called cosmological redshift, and it's different from the Doppler redshift that Slipher was measuring. Doppler redshift occurs when an object moves through space compressing or stretching the light waves by its motion. Cosmological redshift occurs when space itself expands, stretching the light waves as they travel. For nearby galaxies like those Slipher observed, the distinction doesn't matter much. The math works out roughly the same. But for very distant galaxies, the difference becomes crucial. A galaxy 10 billion light-years away isn't moving through space at some fraction of light speed. It's essentially stationary in its local patch of space, but the space between us and that galaxy has expanded so much that the light reaching us has been stretched to nearly double its original wavelength. Here's where it gets truly fascinating. We can actually measure how much the universe has expanded since a photon began its journey by looking at its redshift. Astronomers use a value called Z, the redshift parameter. A redshift of Z equals 0 means no expansion, the object is at rest relative to us. A redshift of Z equals 1 means the universe has doubled in size since the light was emitted. The wavelength of the light has doubled. A redshift of Z equals 2 means the universe has tripled in size. The most distant galaxies we've observed have redshifts of Z equals 10 or higher, meaning the universe has expanded more than 10 times since their light began traveling toward us. Think about what this means. When you look at a galaxy with a redshift of Z equals 1, you're not just seeing it as it was in the past. You're seeing light that has been stretched by the expansion of space itself. That galaxy might have emitted blue light, but by the time it reaches us, the expansion of the universe has stretched those blue wavelengths into red. The galaxy hasn't changed color. The universe has changed the light's color by expanding. Now, let's talk about what redshift tells us about cosmic history. In 1929, Hubble published a graph that would become one of the most important images in astronomy. On the horizontal axis, he plotted distance to galaxies. On the vertical axis, he plotted their recession velocities as measured by redshift. The result was a straight line. Distance and velocity were directly proportional. This was Hubble's law, and it was the smoking gun evidence for cosmic expansion. But Hubble's original graph was frankly a mess. He only had data for 24 galaxies, and the scatter was enormous. Some galaxies didn't fit the line at all. His distance measurements were wildly inaccurate because he was using the wrong type of stars as distance markers. He calculated that the universe was expanding at a rate of about 500 kilometers per second per megaparsec, which implied the universe was only 2 billion years old. This was embarrassing because geologists had already determined the Earth was at least 3 billion years old. How could the Earth be older than the universe? It took decades to sort this out. By the 1950s, astronomers had discovered Hubble's error. He had confused two different types of variable stars, Cepheids that had different intrinsic brightnesses. When they recalculated distances using the correct stars, the expansion rate dropped to about 180 kilometers per second per megaparsec, giving an age of about 7 billion years. Still too young, but getting better. By the 1990s, using the Hubble Space Telescope to observe Cepheids and distant galaxies, astronomers refined the expansion rate to about 70 kilometers per second per megaparsec, giving a universe age of about 14 billion years. That matched other independent measurements and solved the age problem. Today we measure the expansion rate called the Hubble constant, with extraordinary precision using multiple methods. Observations of the cosmic microwave background radiation give a value of about 67 kilometers per second per megaparsec. Observations of distant supernovae give about 73 kilometers per second per megaparsec. These two methods don't quite agree, and this disagreement is one of the biggest mysteries in modern cosmology. It suggests either our measurements have systematic errors we haven't found, or there's new physics we don't understand affecting cosmic expansion. But that's a story for another time. What matters here is that redshift gives us a window into cosmic history. Every galaxy's redshift is like a timestamp, telling us when its light began traveling toward us, and how much the universe has expanded since then. The most distant galaxy ever observed as of recent measurements has a redshift of about Z equals 13.2. This galaxy, called HD 1, emitted its light only about 330 million years after the Big Bang, when the universe was just 2.4% of its current age. The light from HD1 has been traveling for 13.47 billion years, and during that journey, the universe has expanded more than 14 times. The blue and ultraviolet light emitted by young hot stars in HD1 has been stretched into infrared wavelengths by the time it reaches our telescopes. Here's something that often confuses people. If HD1 is 13.47 billion light years away in light travel distance, does that mean it's 13.47 billion light years away in actual distance right now? No, because space has been expanding while the light was traveling. HD1 is now about 33.4 billion light years away. The galaxy has been carried away from us by the expansion of space during the 13.47 billion years its light took to reach us. This is the difference between light travel distance and co-moving distance, and it's crucial for understanding the size of the observable universe. Let me give you another example to make this concrete. Imagine you're on a moving walkway at an airport, one of those conveyor belts that helps you walk faster. You start walking at 1 meter per second, and the walkway itself is moving at 1 meter per second. Your total speed relative to the ground is 2 meters per second. Now imagine you're walking against the direction of the walkway. You walk at 1 meter per second, but the walkway carries you backward at 1 meter per second. Your total speed relative to the ground is 0. You're walking, but going nowhere. Light traveling through expanding space is like a person walking on a moving walkway that's accelerating. The light moves toward us at 300,000 kilometers per second, the cosmic speed limit. But space itself is expanding, carrying the galaxy that emitted the light farther away. For nearby galaxies, the expansion is slow, and light makes steady progress toward us. For very distant galaxies, the expansion is so fast that light makes only slow progress, or, in some cases, no progress at all. There's a distance beyond which space is receding faster than light can cross it, and light from galaxies beyond. That distance will never reach us, no matter how long we wait. This brings us to one of the most profound implications of redshift. The farther we look into space, the farther we look back in time. Light is our time machine. When we observe a galaxy 10 billion light years away, we see it as it was 10 billion years ago, when the universe was younger, denser, hotter. The galaxies we see in the deep past look different from modern galaxies. They're smaller, more irregular, more actively forming stars. By measuring redshifts of thousands of galaxies at different distances, astronomers have reconstructed the history of the universe, watching galaxies grow and evolve over billions of years. And here's something beautiful. Every photon that reaches your eye from a distant star or galaxy carries a record of its journey through space. Its color has been shifted by the expansion of the universe. Its path has been bent by the gravity of intervening matter. Its polarization has been affected by magnetic fields. Each photon is a messenger carrying information about the cosmos, written in its wavelength, direction, and energy. Redshift is just one word in that cosmic language, but it's perhaps the most important word. It tells us the universe is expanding, that it had a beginning, that it's evolving toward a future we can calculate. Think about Vesto Slipher, standing at his telescope in 1912, photographing spectra, night after night, patiently measuring the positions of absorption lines. He had no idea he was witnessing the expansion of the universe. He thought he was measuring the rotation of nearby nebulae, but his careful, methodical work laid the foundation for Hubble's discovery 17 years later. Science is often like this. We stumble upon profound truths while searching for something else entirely. The universe reveals its secrets in whispers, encoded in colors, waiting for patient observers to decode them. As you close your eyes tonight, remember that the light reaching Earth from distant galaxies has been traveling for billions of years, stretched by the expansion of space carrying messages about the universe's history. Every wavelength tells a story. Every redshift is a measurement of cosmic time. And all of it is happening right now, photons raining down from the sky, whispering secrets about the expanding cosmos. But redshift tells us that space is expanding. It doesn't tell us what space actually is. What is this fabric that can stretch and grow? What is the substrate of reality itself? That question takes us into even stranger territory. Right now, between you and the wall of your room, there's something. Not air, though air is there too. Not electromagnetic fields, though, those permeate everything. I'm talking about space itself, the stage on which reality performs. We've talked about how this space expands, how it stretches and grows, carrying galaxies apart. But we haven't asked the most fundamental question of all: what is space? Is it truly nothing, just empty void? Or is it something a substance with properties and structure? This question haunted physicists for centuries, and the answer they finally discovered is so strange, so counterintuitive that it challenges everything we think we know about the difference between something and nothing. Because it turns out that empty space isn't empty at all. It's seething with activity filled with energy, and it can do things that seem to violate the most basic laws of physics. If you want to understand what space really is, what this invisible substrate of reality consists of, go ahead and like this video. And subscribe to continue this journey into the deepest mysteries of the cosmos, where nothing turns out to be everything. Let's go back to ancient Greece to around 450 BCE, when a philosopher named Leucippus proposed something radical. Everything he said is made of atoms and void. Atoms were tiny, indivisible particles of matter. Void was the empty space between them, the nothingness that allowed atoms to move and rearrange themselves. His student Democritus developed this idea, further arguing that the void must exist, because without it, atoms would have nowhere to move. Motion requires empty space. But another philosopher, Parmenides, disagreed violently. Nothing cannot exist, he argued, because existence is a property of something. The very concept of nothing is contradictory. If the void exists, then it's something not nothing. And if it doesn't exist, then how can we talk about it? This paradox troubled Greek philosophy for centuries. Aristotle sided with Parmenides, declaring that nature abhors a vacuum. The universe must be completely filled with substance, he claimed. There could be no such thing as truly empty space. This debate wasn't just philosophical. It had practical implications. In 1643, Italian scientist Evangelista Torricelli created the first sustained vacuum by filling a tube with mercury and inverting it into a bowl of mercury. The mercury in the tube dropped, leaving a space above it with no air, no matter nothing. What was in that space? Aristotelian philosophers insisted it must be filled with some invisible substance. But Torricelli disagreed. It was empty space, he said. True void. The debate intensified in the 19th century when physicists discovered that light is an electromagnetic wave. Waves need a medium to propagate through, just as sound waves propagate through air, and water, waves propagate through water. So, what medium did light waves propagate through? Scientists proposed the existence of the luminiferous ether, an invisible massless substance that permeated all of space. Light waves were vibrations in this ether, just as sound waves were vibrations in air. In 1887, Albert Michelson and Edward Morley designed an experiment to detect the ether. The Earth moves through space at about 30 kilometers per second as it orbits the Sun. If space is filled with ether, then the Earth must be moving through this ether, creating an ether wind, just as a car moving through still air creates wind. Michelson and Morley used an interferometer, a device that splits a beam of light and sends the two beams on perpendicular paths before recombining them. If there was an ether wind light traveling parallel to the wind, should take a different amount of time than light traveling perpendicular to it, creating an interference pattern. They measured nothing. No ether wind, no difference in light speed, regardless of direction. The result was so unexpected that Michelson called it a failure. He spent the rest of his life trying to explain it. Other scientists proposed increasingly elaborate modifications to ether theory. Maybe the Earth drags the ether along with it. Maybe the ether has different properties than we thought. The solution came in 1905 when Albert Einstein published his special theory of relativity. There is no ether, Einstein declared. Light doesn't need a medium to propagate through. It propagates through empty space at a constant speed the same in all directions, regardless of the motion of the source or observer. Space is not a substance. It's simply the distance between objects, the stage on which events occur. This was revolutionary. For the first time in history, physicists accepted that truly empty space could exist, and that it had definite properties. Light traveled through it at exactly 299,792,458 meters per second, not because space was made of anything, but because that's simply how space-time is structured. But Einstein's general relativity, published in 1915, complicated this picture dramatically. Space wasn't just an empty stage anymore. It was a dynamic, flexible fabric that could be warped and curved by the presence of mass and energy. Imagine a bowling ball placed on a stretched rubber sheet. The ball creates a depression, curving the sheet around it. Nearby marbles will roll toward the bowling ball, not because of any force pulling them, but because they're following the curved surface. That's gravity in general relativity. Massive objects curve space-time, and other objects follow the straightest possible paths through this curved space-time, which appear to us as orbits in falling motion. So, is space something or nothing? Einstein's answer was subtle. Space by itself, separate from time, isn't well defined in relativity. What exists is space-time, a four-dimensional fabric that combines space and time into a single entity. This fabric has geometry, structure, curvature. It's not a substance in the traditional sense. You can't grab a handful of space-time. But it's not nothing either. It has measurable properties. It can be bent, stretched, rippled. When massive objects accelerate, they create gravitational waves, ripples in space-time, that propagate outward at the speed of light. These waves were directly detected for the first time in 2015, exactly 100 years after Einstein predicted them. But here's where quantum mechanics throws a wrench into everything. In the 1920s, physicists discovered that the quantum world is governed by uncertainty. Heisenberg's uncertainty principle says, you cannot simultaneously know both the position and momentum of a particle with perfect precision. The more precisely you know one, the less precisely you can know the other. This isn't a limitation of measurement tools. It's a fundamental property of reality. This uncertainty applies to fields as well as particles. And remember, in quantum field theory, space is filled with fields. The electromagnetic field permeates all of space. So do the electron field, the quark field, and many others. Particles are just localized excitations of these fields, like waves on an ocean. But here's the weird part. Even in regions of space where there are no particles, no excitations, the fields themselves are still there. And because of quantum uncertainty, these fields can never be perfectly still at zero. They fluctuate randomly, constantly creating temporary particles that pop into existence and vanish again almost instantly. These are called virtual particles, and they're not hypothetical. They have measurable effects. In 1948, Dutch physicist Hendrik Casimir predicted that if you place two uncharged metal plates very close together in a vacuum, they will experience an attractive force. Why? Because the vacuum between the plates and the vacuum outside the plates are different. The space between the plates can only support virtual particles with certain wavelengths, those that fit between the plates like standing waves on a string. The space outside the plates has no such restriction and supports virtual particles of all wavelengths. This creates a difference in vacuum energy density, and that difference produces a measurable force pushing the plates together. In 1996, physicist Steve Lamoureux finally measured the Casimir effect with enough precision to confirm Casimir's prediction. The force is tiny, about equal to the weight of a blood cell over an area the size of a fingernail. But it's real, empty space even when you remove all matter, all radiation, everything still has energy. The vacuum isn't empty. It's a seething foam of virtual particles constantly appearing and disappearing, borrowing energy from the uncertainty principle and paying it back before the universe notices. How much energy? This is where things get truly bizarre. When physicists try to calculate the energy density of empty space using quantum field theory, they get an answer that's infinite. That's obviously wrong. Space doesn't have infinite energy. So they use a trick called renormalization, cutting off the calculation at very short distances to get a finite answer. But even with this cutoff, the calculated vacuum energy is about 10 to the power of 120 times larger than the observed vacuum energy. This is the worst prediction in the history of physics, off by a factor of 1 followed by 120 zeros. We have no idea why the vacuum energy is so much smaller than quantum mechanics predicts it should be. This is called the cosmological constant problem, and it's one of the deepest mysteries in physics. Let me paint you a picture of what quantum field theory says the vacuum looks like at the smallest scales. Imagine you could zoom in on empty space, magnifying it billions and billions of times down to distances of about 10 to the power of minus 35 meters. This is the Planck length, the smallest distance that has meaning in physics. At this scale, space doesn't look smooth anymore. It looks like a foam constantly bubbling and churning with quantum fluctuations. Virtual particles appear and disappear. The geometry of space-time itself fluctuates wildly. Tiny wormholes might open and close, connecting distant regions of space. This is quantum foam, and it might be what space really is at its most fundamental level. But we can't observe quantum foam directly. It exists at scale far too small for any microscope or particle accelerator to reach. It's a prediction of theory, an inference from mathematics. We assume space is smooth because that's how it appears at the scales we can measure. But maybe smoothness is an illusion, an approximation that breaks down when you look closely enough. Here's another strange property of space that quantum mechanics reveals. The vacuum can conduct electricity, sort of. If you create an extremely strong electric field, strong enough to reach about 10 to the power of 18 volts per meter, the vacuum itself breaks down. Electron-positron pairs are ripped out of the vacuum, suddenly becoming real particles instead of virtual ones. This is called the Schwinger effect. And while we can't create fields this strong in laboratories yet, we think they exist near the event horizons of black holes and in the cores of neutron stars. So, what is space? After all this, can we answer the question? Space, or more accurately, space-time, is the four-dimensional fabric that provides the stage for reality. It has geometry and can be curved by mass and energy. It's filled with quantum fields that fluctuate constantly, creating temporary particles, even in regions with no matter. It has a small but non-zero energy density that we call dark energy, which drives the acceleration of cosmic expansion. It can stretch, expand, ripple with gravitational waves, and possibly even tear or reconnect in quantum foam. Space is not nothing, but it's not something in the way that matter is something. It's the substrate of reality, the framework within which matter and energy exist and interact. And here's what makes it so profoundly strange. This substrate can grow. New space can be created. The fabric of space-time can expand, stretching the distance between galaxies, and this expansion doesn't violate conservation of energy because the expanding space carries negative gravitational energy that exactly balances the positive energy of matter. Think about what this means. The The universe isn't just expanding into some pre-existing void. The expansion is creating new space-time itself. More of the substrate of reality is coming into existence every moment. Between the time you started listening to this section and now, billions of cubic kilometers of new space have been created in the observable universe. This space didn't exist before. It exists now, and it will continue to exist even as more space is created around it. Can space be destroyed? We don't know. Black holes might destroy space, crushing it into a singularity where space-time curvature becomes infinite and the laws of physics break down. Or maybe space can't be destroyed, only transformed. These are open questions. We're still learning what space is at its most fundamental level. Here's a thought experiment that might help crystallize this. Imagine you're a character in a video game. From your perspective inside the game, you perceive a world with distance, duration, physical laws. But from the perspective of someone outside the game, looking at the computer running it, the game world doesn't exist in physical space at all. It exists as information, as data structures in computer memory. The space you perceive in the game is just a way of organizing that information, giving it structure and relationships. Maybe our universe is similar. Maybe space-time isn't the fundamental reality. Maybe it's an emergent phenomenon, a way of organizing something more fundamental that we don't yet understand. Some physicists are exploring this idea, suggesting that space-time might emerge from quantum entanglement, the strange correlation that can exist between particles. Others suggest space-time might be holographic, with the information content of any region encoded on its boundary rather than in its volume. These are speculative ideas, but they point toward a future where our understanding of space might be as different from Einstein's as Einstein's was from Newton's. For now, though, we can say this space is real. It has properties. And one of those properties is that it can expand. This expansion is happening right now, stretching the fabric of reality, creating new distance between galaxies. And unlike matter, which is constrained by the speed of light, space itself can expand faster than light. There's no law of physics that prohibits it, which leads to a fascinating question. If space can expand faster than light, what does that mean for objects embedded in that space? Can galaxies appear to recede from us faster than light? And if so, what does that tell us about the limits of our observable universe? Let's explore that peculiar paradox. Here's something that should terrify you. The universe is expanding. Space itself is stretching, growing, creating new distance between galaxies. Every second, thousands of kilometers of new space appear. And yet, as you lie in bed right now, you're not being stretched. The distance between your head and your feet isn't increasing. Your bones aren't slowly pulling apart. Your atoms aren't drifting away from each other. The coffee cup on your nightstand, the air molecules in your room, even the moon orbiting Earth, none of these are expanding, despite living in an expanding universe. Why not? If space itself is growing everywhere, shouldn't everything be growing? This puzzle confused physicists for decades, and the answer reveals something profound about the hierarchy of forces in nature and the scales at which cosmic expansion actually matters. If you've ever wondered why you're not being torn apart by the expansion of the universe, hit that like button and subscribe to keep exploring these cosmic questions, where we discover why some things stay together while the universe itself grows. Let's start with a common misconception that appears in popular science all the time. You'll often hear someone say, "The universe is expanding, but don't worry, the expansion only happens between galaxies, not inside galaxies or solar systems or atoms." This makes it sound like expansion has boundaries, like there are regions where space expands and regions where it doesn't. But that's not quite right. The truth is more subtle and more interesting. Space is expanding everywhere uniformly at every point in the universe. Right now, between your hand and this device you're listening on, space is trying to expand. The expansion rate is about 70 kilometers per second per megaparsec. Remember, a megaparsec is 3.26 million light years, which is about 3 times 10 to the power of 19 kilometers. The electromagnetic forces holding atoms together, the gravitational forces holding planets and stars together, even the weak gravitational binding of galaxies, all of these are far, far stronger than the expansion of space at these scales. Here's the key insight. Expansion isn't a force. That's the crucial point that most explanations miss. When we say space is expanding, we're not describing a force pushing things apart. We're describing the natural tendency of space-time geometry to evolve over time, according to Einstein's equations. In the absence of other forces, objects would indeed drift apart as space expands between them. But other forces are present, and they prevent this drift. Think of it like this. Imagine you're standing on a train platform and the train starts moving. In the absence of friction between your feet and the platform, the train would carry you along with it. But friction is present holding your feet to the platform, so you stay put while the train moves away. Cosmic expansion is like the train. Electromagnetic and gravitational forces are like friction, holding things in place despite the expansion trying to carry them apart. Let's look at specific examples to see where expansion matters and where it doesn't. Start with atoms. An atom consists of a nucleus surrounded by an electron cloud. The electrons are bound to the nucleus by electromagnetic force, which at atomic scales is enormously strong. The binding energy of a hydrogen atom, the simplest atom, is about 13.6 electron volts. How much energy would cosmic expansion add to the atom over the age of the universe? The calculation is complex, but physicists have done it. Over 13.8 billion years, the expansion of space would add energy to a hydrogen atom equivalent to about 10 to the power of minus 50 electron volts. That's a decimal point followed by 49 zeros and then a 5. Compare that to the 13.6 electron volts binding the atom together. The expansion is utterly negligible. Atoms don't expand because the electromagnetic force holding them together is incomprehensibly stronger than the cosmic expansion at atomic scales. What about larger structures? Let's consider the Earth-Moon system. The Moon orbits Earth at an average distance of 384,400 kilometers. How much is cosmic expansion trying to increase this distance? Using the Hubble constant, we can calculate that expansion tries to increase the Earth-Moon distance by about 0.0004 millimeters per year. That's 4/10,000ths of a millimeter, about the size of a large bacteria. Meanwhile, the Moon is actually moving away from Earth at about 38 millimeters per year due to tidal forces. The real effect is 95,000 times larger than the expansion effect. Cosmic expansion is irrelevant to the Earth-Moon system because gravitational binding is so much stronger. Let's go bigger. Our solar system spans about 60 astronomical units from the Sun to the orbit of Neptune. 1 astronomical unit is the Earth-Sun distance, about 150 million kilometers. How much does cosmic expansion affect the solar system? The calculation shows that expansion tries to increase the size of the solar system by about 0.00001% per billion years. Meanwhile, the Sun's gravity holds the solar system together with such strength that this expansion is completely negligible. The planets aren't drifting away due to cosmic expansion. They're held in stable orbits by gravity. Even bigger, our Milky Way galaxy is about 100,000 light-years across. Cosmic expansion tries to increase this by about 0.000007 light-years per year. But the Milky Way is held together by its own gravity, the collective gravitational pull of hundreds of billions of stars plus dark matter. The galaxy isn't expanding. In fact, gravity is strong enough that the Milky Way is actually on a collision course with the Andromeda Galaxy, approaching at about 110 kilometers per second, despite the expansion of space. Gravity wins. Here's where it gets interesting. There's a critical scale at which cosmic expansion becomes significant, and it's larger than individual galaxies but smaller than the observable universe. This scale is roughly the size of galaxy cluster structures, containing dozens or hundreds of galaxies bound together by gravity. Our Milky Way is part of a group called the Local Group, which includes Andromeda Triangulum and about 80 smaller galaxies spanning about 10 million light years. The Local Group is gravitationally bound. It's not expanding. The galaxies within it are held together by their mutual gravity, and this binding energy exceeds the expansion energy. But here's the dividing line. The Local Group itself is part of a larger structure called the Virgo supercluster, spanning about 110 million light years. And the Virgo supercluster is not gravitationally bound. The expansion of space is strong enough at this scale to overcome gravity. Galaxy clusters at the edges of the supercluster are drifting apart, carried by expansion. This is the scale where cosmic expansion wins. Why does scale matter so much? It comes down to how gravitational binding energy scales with distance versus how expansion scales with distance. Gravitational binding energy decreases with distance. The farther apart two objects are, the weaker their gravitational attraction. But cosmic expansion increases linearly with distance. The farther apart two objects are, the faster space expands between them. At small scales, gravity dominates. At large scales, expansion dominates. The transition happens somewhere around the scale of galaxy clusters. Let me give you a concrete example. Consider two galaxies 1 megaparsec apart, about 3.26 million light years. Space expands between them at 70 kilometers per second. Now, consider two galaxies 100 megaparsecs apart. Space expands between them at 7,000 kilometers per second. The expansion rate increases with distance, but gravitational force between the galaxies decreases as the square of the distance. So, at 1 megaparsec, maybe gravity can hold them together. At 100 megaparsecs, definitely not. Expansion wins. Here's a thought experiment that makes this clearer. Imagine you have a rubber band stretched between two posts. You start stretching the space between the posts, pulling them apart. At first, the rubber band stays intact, stretching slightly but holding together because its elastic force is strong enough. But keep pulling the posts farther apart, stretching faster and faster, and eventually the elastic force can't keep up. The rubber band breaks. That's what happens in the universe. At small scales, the rubber bands of electromagnetic force and gravity are strong enough to resist expansion. At large scales, they're not. Now, here's something fascinating that often surprises people. There's a common question: will the expansion of the universe eventually overcome atomic forces and tear atoms apart? Will expansion accelerate so much that even the electromagnetic force can't hold electrons to nuclei, causing everything to disintegrate in a big rip? The answer depends on something called dark energy, which we'll talk about later. But here's the key point for expansion to tear atoms apart. The expansion rate itself would have to increase dramatically. Not just the size of the universe growing, but the rate of growth accelerating so much that even at atomic scales, expansion becomes a significant effect. Current observations suggest this probably won't happen. Dark energy appears to be a cosmological constant, meaning the expansion rate per unit distance stays constant even as the universe grows. Under this scenario, bound structures remain bound forever. The expansion rate at atomic scales remains negligibly small for all time. But if dark energy is something more exotic, something that grows stronger over time, then yes, eventually even atoms could be torn apart. We don't know yet. The universe's ultimate fate remains uncertain. Let's talk about a common misconception. People sometimes ask if expansion doesn't affect atoms or solar systems or galaxies, then how do we know it's real? If it's not measurable locally, maybe it's just an illusion created by some other effect. This is actually a profound question, and it troubled astronomers in the early days of cosmology. How can expansion be real if we can't measure it in our own cosmic neighborhood? The answer is that expansion is measurable, just not at small scales. We measure it by observing distant galaxies and seeing how their recession velocity correlates with distance. We measure it through the cosmic microwave background radiation, seeing how the wavelength of ancient light has been stretched by expansion. We measure it through the abundances of light elements created in the Big Bang, which depend on how fast the universe was expanding in its first few minutes. All of these measurements point to the same conclusion. Space is expanding uniformly and has been for 13.8 billion years. But locally in our own galaxy and nearby galaxies, this expansion is indeed unmeasurable because it's so overwhelmed by other effects. It's like trying to measure the curvature of the Earth by looking at your backyard. Your yard looks flat because you're observing at too small a scale. The curvature only becomes apparent when you look at larger scales. Same with cosmic expansion. It only becomes significant at scales of hundreds of millions of light years. Here's another way to think about it. Imagine you're an ant on a balloon that's being inflated. If you're standing on a smooth region of rubber, you'll slowly drift away from other ants as the rubber stretches. But now, imagine you're standing on a spot where someone has drawn a circle and permanent marker. The ink creates a tiny region where the rubber molecules are slightly bonded together. As the balloon inflates, the rubber stretches, but the ink spot doesn't. You're standing in the ink spot so you don't drift. That's us. We're in a gravitationally bound ink spot called the local group. And while the space around us expands, our local neighborhood doesn't participate in that expansion. Does this mean we're special? Not at all. Every galaxy cluster is its own ink spot, held together by gravity while the space around it expands. The universe is like a balloon covered in ink spots of various sizes. The rubber between the spots stretches, but the spots themselves stay intact. We happen to live in one of the spots. Here's something that might surprise you. The division between expanding and non-expanding isn't fixed. It changes over time. Early in the universe's history, when matter density was higher and gravity was relatively stronger compared to the expansion rate, larger structures could remain gravitationally bound. As the universe expands and matter density decreases, the balance shifts. Structures that were once bound might eventually become unbound and start participating in the expansion. Meanwhile, dark energy, which we'll discuss later, is causing the expansion to accelerate, shifting the balance even further toward expansion. The universe is dynamic, evolving, and the boundary between bound and unbound structures shifts over billions of years. Let me leave you with one final thought. You are not expanding. Your atoms are not drifting apart. The electromagnetic forces holding your molecules together, the chemical bonds giving structure to your cells, the gravitational field holding you to the Earth, all of these are immensely stronger than cosmic expansion at your scale. You are a stable structure in an expanding universe held together by forces that have nothing to do with expansion. And yet, you are part of this expanding universe. The space beyond our galaxy, beyond our local group, beyond our supercluster is stretching and growing. Distant galaxies are being carried away by this expansion, receding faster and faster as the distance grows. Some are already receding faster than light. And this raises a peculiar paradox that's worth exploring. How can anything, even galaxies carried by expanding space, move faster than light without violating Einstein's sacred speed limit? That apparent contradiction leads us into some of the strangest territory in all of cosmology. There are galaxies racing away from us right now at twice the speed of light, 3 times the speed of light, 10 times the speed of light. This seems impossible. Einstein's special relativity, one of the most rigorously tested theories in all of physics, tells us that nothing can move faster than light. It's not just a speed limit for matter. It's a fundamental law of causality, the cosmic speed limit that prevents information from traveling instantaneously, that preserves cause and effect, that keeps the universe from descending into paradox. And yet, galaxies are breaking this limit right now. How is this possible? The answer isn't that Einstein was wrong. It's that the universe has found a loophole, a way to make things recede faster than light without actually violating relativity at all. This paradox confused even professional physicists for decades, and understanding its resolution reveals something profound about the nature of cosmic horizons and the limits of what we can ever see, ever know, ever reach. If you want to understand how the universe can break its own speed limit without actually breaking it, go ahead and hit that like button. And subscribe to continue unraveling these cosmic paradoxes where impossible things turn out to be perfectly legal. Let's start with Einstein's speed limit and understand exactly what it says. In 1905, Einstein published his special theory of relativity, which established that the speed of light in vacuum, about 299,792 kilometers per second, is the same for all observers, regardless of their motion. This seems simple, but it has radical implications. If everyone measures light at the same speed, then space and time must be flexible, adjusting themselves to make this true. What looks like 1 meter to you might look like a different length to someone moving relative to you. What looks like 1 second to you might look like a different duration to them. Space and time are relative. Only the speed of light is absolute. From this follows a crucial consequence: nothing with mass can reach or exceed the speed of light. As an object accelerates, its energy increases. But instead of all that energy going into speed, more and more of it goes into increasing the object's mass, or more precisely, its relativistic mass. To accelerate a massive object to light speed would require infinite energy. It's impossible. Light itself can travel at light speed, only because photons have no mass. Anything with mass must travel slower than light. This is the cosmic speed limit. But here's what Einstein actually said, and this is crucial: nothing can move through space faster than light. The speed limit applies to motion through space. It doesn't apply to space itself. Space isn't moving through anything. Space is the stage on which motion occurs. And there's no law of physics that prevents the stage from expanding, even expanding faster than light. Think about it this way. Imagine you're on a moving walkway at an airport, one of those conveyor belts. You walk forward at, let's say, 1 meter per second. The walkway moves at 1 meter per second. Relative to the ground, you're moving at 2 meters per second. Now, imagine the walkway starts accelerating. It moves at 2 meters per second, then 3, then 5. You're still walking at 1 meter per second. Relative to the walkway, but relative to the ground, you're moving faster and faster. Have you violated any law of physics by moving faster than your walking speed? Of course not. The walkway is carrying you. That's what happens with cosmic expansion. Galaxies aren't moving through space at faster than light speeds. They're essentially stationary in their local patch of space. But space itself is expanding between us and them, carrying them away. And because space can't expand at any rate, galaxies can appear to recede faster than light without violating relativity. But let's be more precise about what this means. There's a distance called the Hubble radius, or Hubble sphere, beyond which galaxies recede faster than light due to expansion. Remember that the expansion rate is about 70 kilometers per second per megaparsec. So, for every 3.26 million light-years of distance recession velocity increases by 70 kilometers per second. Light speed is 300,000 kilometers per second. So, at what distance does recession velocity equal light speed? We can calculate it: 300,000 divided by 70 times 3.26 million light-years equals about 14 billion light-years. That's the Hubble radius. Everything beyond this distance is receding faster than light. Now, here's where it gets strange. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, has a radius of about 46 billion light-years. Wait, how can that be? If the universe is 13.8 billion years old, shouldn't light have traveled a maximum distance of 13.8 billion light-years? The answer is expansion. Light that was emitted from a galaxy 13.8 billion years ago has been traveling toward us for 13.8 billion years. But during that time, space has been expanding. The galaxy that emitted the light has been carried away by expansion. That galaxy is now about 46 billion light-years away. and the light from its current position will never reach us because the space between us is expanding faster than light can cross it. This creates cosmic horizons boundaries beyond which we cannot see, cannot communicate, cannot ever reach. These horizons are not physical barriers. There's no wall at the edge of the observable universe. It's simply that light from beyond a certain distance cannot reach us because expansion carries those regions away faster than light can travel toward us. Let me make this concrete with a specific example. In 2016, astronomers using the Hubble Space Telescope discovered a galaxy called GN-Z11. Its light has been traveling for 13.4 billion years. When the light we're seeing now was emitted, the galaxy was about 2.7 billion light years away from the location in space that would eventually become the Milky Way. But during those 13.4 billion years, space has been expanding. Today, GN-Z11 is about 32 billion light years away. And here's the key point right now. GN-Z11 is receding from us at about 2.2 times the speed of light. We can see it only because we're observing light that was emitted when the galaxy was much closer before expansion carried it beyond our cosmic horizon. Could we ever travel to GN-Z11? Even if we could somehow travel at light speed, the answer is no. By the time we reach the location where GN-Z11 is now, it would have been carried even farther away by expansion. We would be chasing a receding target like running on a treadmill that's accelerating faster than we can run. GN-Z11 is forever beyond our reach, not because it's too far in space, but because the space between us is growing too fast. This leads to one of the most unsettling facts about cosmology. There are galaxies that exist right now, galaxies filled with stars and planets, and possibly even life that we will never see. Their light will never reach us, not because they're too faint, but because the space between us is expanding faster than their light can cross it. These galaxies are beyond our cosmic horizon, causally disconnected from us. For all practical purposes, they don't exist in our universe. We exist in separate non-overlapping portions of space-time. How many galaxies are beyond our horizon? Current estimates suggest that the observable universe contains about 2 trillion galaxies. But the entire universe, the whole cosmos beyond what we can see, might contain infinitely many more. Some cosmologists estimate there could be 10 to the power of 23 galaxies in the entire universe, meaning we can see only about 1/1000% of all galaxies. The rest are beyond our horizon, forever invisible, forever unreachable. Now, let's talk about another horizon, one that's even more fundamental. It's called the particle horizon, and it represents the boundary of the observable universe itself. Light from beyond the particle horizon simply hasn't had time to reach us yet since the Big Bang. Every year, as the universe ages, this horizon expands. Light from slightly more distant regions reaches us for the first time. We see a tiny bit more of the universe each year. But here's the twist. Because the expansion of the universe is accelerating, which we'll discuss in detail later, there's another horizon called the cosmic event horizon. This is the boundary beyond which events happening right now will never be visible to us in the future, no matter how long we wait. Light from beyond this horizon is being emitted right now, traveling toward us, but the expansion of space is carrying those regions away faster than the light can approach us. That light will never arrive. The cosmic event horizon is currently about 16 billion light years away, slightly farther than the Hubble sphere. Think about what this means. There are stars exploding into supernovae right now beyond our event horizon, whose light will never reach Earth. There might be civilizations arising, building their own telescopes, looking out at their own cosmic horizon. We will never know they exist. They will never know we exist. The universe has isolated us from them permanently, not by distance alone, but by the geometry of expanding space-time itself. Here's a thought experiment that makes this clearer. Imagine you're standing on a beach and the tide is going out. You're trying to reach a buoy floating in the ocean. You run toward it at your maximum speed, let's say 5 meters per second, but the tide is carrying the buoy away at 10 meters per second. You can see the buoy. You can watch it bobbing on the waves, but you can never reach it because it's receding faster than you can run. That's us in distant galaxies. We can see them with our telescopes, we can study their light, measure their properties, but we can never visit them because space is expanding faster than we could ever travel. Does this mean faster than light travel is possible? No, not in the sense that most people imagine. You cannot build a spaceship that accelerates through local space faster than light. That would violate relativity and create causality paradoxes. But there are theoretical proposals like the Alcubierre drive that suggest you might be able to contract space in front of you and expand it behind you, creating a warp bubble that moves through space faster than light, without you ever moving through your local space faster than light. You would be surfing on a wave of space-time itself, much like galaxies surf on the expansion of the universe. Is this practical? Almost certainly not. The Alcubierre drive requires exotic matter with negative mass energy, which probably doesn't exist. Even if it did exist, the energy requirements would be astronomical, possibly requiring more energy than exists in the observable universe. It's a mathematical curiosity, a solution to Einstein's equations that probably has no physical realization. But it illustrates the principle the speed limit applies to motion through space, not to the motion of space itself. Let's return to the original question. How can galaxies recede faster than light without violating relativity? Because relativity doesn't prohibit it. The speed limit in special relativity applies to objects moving through space-time, measured in a local inertial reference frame. A galaxy beyond our Hubble sphere is not moving through space at faster than light speed. If you were standing on a planet in that galaxy looking around at your local neighborhood, you would measure nothing moving faster than light. The galaxy is essentially at rest in its local space, but the space between us and that galaxy is expanding, and expansion has no speed limit. Here's an analogy that might help. Imagine you have a ruler made of rubber. You mark 2 points on the ruler 1 centimeter apart. Now you stretch the ruler. The distance between the 2 points increases, but neither point has moved along the ruler. They're both still at the same position on the rubber. The rubber itself has stretched. That's cosmic expansion. The galaxies are like the marks on the rubber. They're not moving through space. The space between them is growing. What would happen if you tried to send a signal to a galaxy beyond your cosmic horizon? Let's say you point a powerful laser at such a galaxy and send a message. What happens? The light from your laser travels outward at 300,000 kilometers per second, but it's traveling through expanding space. Every second new space appears between your laser and the distant galaxy. If the expansion rate is high enough, the light makes no net progress toward the galaxy. It's like running on a treadmill set faster than you can run. You're running forward, but relative to the ground, you're moving backward. The light from your laser would never reach the galaxy. It would be redshifted by expansion, its wavelength stretching longer and longer, its energy decreasing until it becomes undetectable. This has profound implications for the far future of the universe. As expansion continues and accelerates, more and more galaxies will cross our cosmic event horizon. In about 150 billion years, assuming current models are correct, all galaxies outside our local group will have crossed this horizon. Any civilization arising in the Milky Way at that time will look out and see only the stars of their own galaxy and the few nearby galaxies in the local group. The rest of the universe will have vanished from view, not because the light has stopped, but because the expansion has carried those galaxies beyond the reach of light. Those future astronomers would measure the cosmic microwave background radiation and find it has been redshifted into invisibility. They would have no evidence of the Big Bang, no evidence of cosmic expansion, no evidence that the universe is anything other than their small local group of galaxies surrounded by empty space. They would reach entirely different conclusions about cosmology, and they would be wrong not because they made mistakes, but because the evidence has been erased by expansion. We are lucky. We live at a time when the universe still shows us its history. The cosmic microwave background is still visible. Distant galaxies still reveal the expansion. But this window is temporary. Expansion is slowly closing it. In the deep future, the universe will have expanded so much that all evidence of its origin will have disappeared beyond unreachable horizons. Think about this as you settle into sleep. Right now, at this very moment, there are galaxies receding from us at 10 times the speed of light. There are regions of space beyond our cosmic horizon where entirely separate cosmic histories are unfolding, forever disconnected from ours. And there are future civilizations who will never know about us, who will look out at a dark, nearly empty universe and wonder if they're alone. The paradox of faster-than-light recession reveals something fundamental about the universe. It's bigger and stranger than we can ever see, with horizons that limit not just what we can observe, but what we can ever know. But knowing there are limits raises another question. What's driving all this expansion in the first place? Why is space expanding at all, and why is it accelerating? The answer involves one of the deepest mysteries in physics. 68% of the universe is made of something we can't see, can't touch, can't detect directly, and don't understand at all. It's not dark matter, that mysterious substance that provides the gravitational scaffolding for galaxies. This is something even stranger. It's called dark energy, and it's pushing the universe apart with ever-increasing force. In 1998, two teams of astronomers made a discovery so shocking that it won them the Nobel Prize. 13 years later, the expansion of the universe isn't slowing down as everyone expected. It's speeding up. Galaxies are accelerating away from each other, driven by some mysterious energy that permeates all of space. This discovery didn't just change cosmology. It revealed that we don't understand what most of the universe is made of. We're living in a cosmos dominated by an invisible force that might determine the ultimate fate of everything that exists. If you want to understand the mysterious force that's accelerating the expansion of the universe that makes up more than 2/3 of all cosmic energy, give this video a like. And subscribe to explore the deepest mysteries of the cosmos, where what we don't know is far more than what we do. Let's set the stage for one of the most important discoveries in the history of astronomy. It's the mid-1990s. Cosmologists think they understand the big picture of cosmic evolution. The universe began with the Big Bang 13.8 billion years ago. It's been expanding ever since. But gravity has been slowing that expansion down, like friction slowing a rolling ball. The question astronomers are trying to answer is, how much is gravity slowing the expansion? Is it slowing enough that the universe will eventually stop expanding and collapse back on itself in a big crunch? Or will it expand forever, gradually slowing, but never quite stopping? To answer this, astronomers need to measure how the expansion rate has changed over cosmic history. And the best way to do that is to observe very distant supernovae, exploding stars that can be seen across billions of light years. Specifically, they're looking for Type 1, a supernovae, a special class of stellar explosion that always releases roughly the same amount of energy. Because these supernovae have a known intrinsic brightness, astronomers can use them as standard candles to measure cosmic distances. The idea is elegant. Observe a supernova, measure how bright it appears, and you can calculate how far away it is. Measure its redshift, and you know how fast it's receding due to cosmic expansion. Plot distance against redshift for many supernovae at different distances, and you can map out the expansion history of the universe. If gravity is slowing, the expansion-distant supernovae should appear slightly brighter than expected, because the universe was expanding faster in the past, meaning those supernovae are slightly closer than they would be if expansion were constant. Two independent teams set out to do this measurement in the 1990s. One team, the Supernova Cosmology Project, was led by Saul Perlmutter, at Lawrence Berkeley National Laboratory. The other, the High Z Supernova Search Team, was led by Brian Schmidt at Australian National University and Adam Rees at Space Telescope Science Institute. Both teams were hunting for distant supernovae, measuring their brightness and redshift with painstaking precision. And both teams found something completely unexpected. The distant supernovae were fainter than predicted, not brighter as they would be if gravity were slowing the expansion. Fainter. This could only mean one thing: the supernovae were farther away than expected. The universe had expanded more than predicted. Instead of slowing down, the expansion was speeding up. The first reaction was disbelief. Both teams checked and rechecked their data, looking for errors. Maybe dust between us and the supernovae was dimming their light. No dust would also redden the light, and that wasn't observed. Maybe distant supernovae were intrinsically different from nearby ones, slightly dimmer for some unknown reason. Possible but unlikely, and further observations ruled it out. Maybe there was some systematic error in the measurements. Both teams scrutinized their methods and found nothing wrong. The conclusion was unavoidable. The universe's expansion is accelerating. In 1998, both teams published their results. The announcement was met with widespread skepticism. Accelerating expansion contradicted everything cosmologists thought they knew. It meant that some unknown force was pushing the universe apart, overwhelming gravity's attraction. What could this force be? Where was the energy coming from? The universe seemed to be violating conservation of energy, creating new energy out of nothing to drive the acceleration. But over the following years, as more supernovae were observed and analyzed, the evidence became overwhelming. By 2003, hundreds of supernovae confirmed the acceleration. Other independent lines of evidence from the cosmic microwave background and from large-scale structure surveys also pointed to the same conclusion. The universe's expansion is definitely accelerating, and it has been for the past 6 billion years or so. Before that, for the first 7 to 8 billion years, after the Big Bang, gravity dominated and the expansion was decelerating. But at some point, this mysterious accelerating force took over. Physicists name this force dark energy. Though the name is somewhat misleading, it's not dark in the sense of being invisible. It doesn't interact with light at all. And it's not energy in the traditional sense of something that can be localized or contained. It's more like a property of space itself, a pressure or tension that pushes space apart. But the name stuck, and dark energy entered the cosmological lexicon as one of the greatest mysteries in physics. In 2011, Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics for their discovery. The Nobel Committee called it one of the most astounding discoveries in the history of science. And they were right. Dark energy makes up about 68% of the total energy content of the universe. Dark matter, that other mysterious substance we can't see directly, makes up about 27%. Ordinary matter, the stuff we're made of, everything we can see and touch, makes up only about 5%. We live in a universe where 95% of the content is completely unknown to us. So, what is dark energy? The honest answer is we don't know. But there are several competing hypotheses, each with its own implications for the future of the cosmos. The simplest explanation, and the one that's currently favored by most cosmologists, is that dark energy is the cosmological constant, that same term Einstein added to his equations in 1917, and later called his biggest blunder. Remember, Einstein introduced the constant to keep the universe static. He abandoned it when Hubble discovered expansion. But it turns out that a cosmological constant with the right value doesn't make the universe static. It makes the expansion accelerate. What is the cosmological constant physically? In this interpretation, it's the energy density of empty space itself. The vacuum energy we talked about earlier when discussing quantum foam. Quantum mechanics says that even empty space has energy, a baseline level that can never be reduced to zero. This vacuum energy creates a negative pressure, a kind of tension that pushes space apart. The more space you have, the more vacuum energy you have, and the stronger the push. This creates a runaway effect. Expansion creates more space, which contains more vacuum energy, which drives faster expansion, which creates even more space, and so on. The problem is that when physicists try to calculate the vacuum energy using quantum field theory, they get an answer that's 10 to the power of 120 times too large. This is the cosmological constant problem we mentioned before, the worst prediction in the history of physics. We don't know why the vacuum energy is so much smaller than quantum mechanics predicts. Some unknown mechanism must be canceling out almost all of it, leaving only a tiny residual amount that's driving the acceleration we observe. What that mechanism is remains one of the deepest unsolved problems in theoretical physics. But there are other possibilities. Maybe dark energy isn't a constant at all. Maybe it's a dynamic field, something that changes over time and space. One hypothesis calls this quintessence after the fifth element of ancient Greek philosophy. Quintessence is imagined as a slowly rolling scalar field, similar to the Higgs field that permeates the universe. As the field evolves, it can drive accelerating expansion. Unlike the cosmological constant, which has the same energy density everywhere, and at all times, quintessence can vary. This would make the acceleration rate change over time, something that future observations might be able to detect. Another possibility is that we don't fully understand gravity on cosmic scales. General relativity works extraordinarily well in the solar system, and even in describing binary pulsars and black holes. But maybe gravity behaves differently over distances of billions of light years. Several theories of modified gravity have been proposed that could explain cosmic acceleration without invoking dark energy. These theories modify Einstein's equations in subtle ways that only matter on the largest scales. So far, observations have favored dark energy over modified gravity, but the question isn't completely settled. Here's something that often confuses people. Dark energy is causing the expansion to accelerate, meaning galaxies are receding faster and faster over time. But remember, individual galaxies aren't accelerating through space. Each galaxy is essentially at rest in its local patch of space. What's accelerating is the rate at which space itself is expanding. Think of it like compound interest. The more money you have, the more interest you earn, which gives you more money, which earns even more interest. Similarly, the more space you have, the more dark energy you have, which creates more space, which contains more dark energy. What does this mean for the future? If dark energy is truly a cosmological constant, unchanging over time, then we can predict the universe's fate with some confidence. The acceleration will continue forever. Galaxies will recede faster and faster. Eventually, in about 150 billion years, all galaxies outside our local group will cross our cosmic event horizon, disappearing from view. The cosmic microwave background radiation will be redshifted into invisibility. Future civilizations will look out at a dark, nearly empty universe containing only their own galaxy and a few nearby companions. But it gets worse, much worse. In about 100 trillion years, star formation will end as galaxies exhaust their gas supplies. The stars that exist will gradually burn out. The universe will enter what's called the degenerate era, dominated by stellar remnants, white dwarfs, neutron stars, black holes. These remnants will slowly decay over unimaginable time scales. Protons might decay in about 10 to the power of 40 years, though this is uncertain. Black holes will evaporate via Hawking radiation, with the supermassive black holes at galaxy centers, taking about 10 to the power of 100 years to vanish completely. Eventually, in the incomprehensibly distant future, the universe will reach a state called heat death. All structure will have dissolved. All energy gradients will have been erased. The universe will be a cold, dark, nearly empty expanse, with a temperature just barely above absolute zero, containing only a thin soup of photons and elementary particles all receding from each other due to eternal expansion. No stars, no planets, no galaxies, no life. just darkness and silence forever. This is sometimes called the Big Freeze scenario, and it's the most likely fate of our universe if current understanding is correct. It's profoundly depressing in a way, but also strangely beautiful. The universe, having blazed into existence in a moment of infinite energy and density, will slowly fade into an eternity of darkness and cold, expanding forever, its last light dying out like embers in an infinite night. But there's another possibility, one that's much more dramatic. What if dark energy isn't constant? What if it's growing stronger over time? If the repulsive force of dark energy increases, the acceleration could become extreme. Eventually, the expansion could become so violent that it overcomes not just gravity holding galaxy clusters together, but gravity holding galaxies together, then solar systems, then planets, then molecules, then atoms. This is called the Big Rip scenario. In the Big Rip, the universe tears itself apart. About 50 million years before the end, galaxies would be ripped apart, their stars flung into the void. 3 months before the end, solar systems would be torn apart, planets ripped from their orbits. Half an hour before the end, planets themselves would disintegrate. In the final fraction of a second, atoms would be torn apart, electrons ripped from nuclei. The universe would end not in fire or ice, but in a catastrophic dissolution of all structure, all matter, everything as the fabric of space-time itself tears. Is the Big Rip our fate? Current observations suggest not. The data indicate that dark energy behaves like a cosmological constant, or at least something very close to it. There's no evidence that it's growing stronger, but we can't rule it out completely. We've only been measuring dark energy for about 25 years. On cosmic timescales, that's nothing. The properties of dark energy could change in the future in ways we can't predict. There's also a third possibility, though. It's less commonly discussed. What if dark energy decays or transforms into something else? What if the vacuum energy that's currently driving acceleration eventually dissipates or changes sign? If dark energy turned off or became negative gravity would once again dominate, and the expansion would slow and eventually reverse. The universe would begin to contract, galaxies would start to approach each other, and eventually everything would collapse back into a big crunch, perhaps, to be followed by a new Big Bang. This cyclic universe model has philosophical appeal, but there's no strong evidence for it. Let me share a personal reflection that many cosmologists have had. When you study dark energy, when you really sit with the implications of what we've discovered, it's humbling in the extreme. We've built telescopes that can see across billions of light years. We've measured the expansion of the universe with this exquisite precision. We've cataloged trillions of galaxies. And yet, we don't understand what most of the universe is made of. We don't know why it's accelerating. We don't know what the future holds. We're like children who have just learned to count, trying to comprehend infinity. But perhaps that's the point. Perhaps the universe is supposed to be mysterious. Perhaps we're not meant to understand everything, at least not yet. The discovery of dark energy didn't answer questions. It opened new ones, deeper ones, questions that might take centuries to resolve. And in doing so, it reminded us that the cosmos is stranger and more wonderful than we ever imagined. As you lie here in the darkness, as your breathing slows and sleep approaches, remember this. The universe is expanding around you, accelerating into an unknown future driven by a force we can't explain. Dark energy is pushing galaxies apart right now, stretching space itself, determining the ultimate fate of everything that exists. And we're here in this brief cosmic moment trying to understand it all, asking questions that echo across the void. That's what makes us human. That's what makes this meaningful. Not knowing everything, but wondering. Always wondering. And that same expansion, that same mysterious force that's determining the cosmic future, also determines how and when the lights finally go out, when the last stars fade and the universe enters its long, final night. That ending is what we need to face next. There will come a time, trillions of years from now, when the last star in the universe flickers and dies, No new stars will form. The galaxies, once brilliant islands of light scattered across the cosmos, will go dark. Black holes will swallow what remains, then slowly evaporate into radiation over timescales so vast they defy comprehension. The universe, having once blazed with the light of 100 billion galaxies, will fade into absolute darkness and cold, expanding forever into an infinite void where nothing happens, nothing changes, nothing exists except the ghost of what once was. This isn't science fiction. This is the most likely fate of our universe according to our best understanding of physics. The universe will not end in fire or catastrophe. It will simply fade away slowly, quietly, until even the memory of stars is erased by time and entropy. If you want to understand the far future of the cosmos, the timeline of how everything ends, hit that like button and subscribe to journey with us through deep time to the very end of everything, where we face the ultimate destiny written in the laws of physics. Let's start with a question that seems simple, but opens vast depths. How long do stars last? Our sun has been shining for about 4.6 billion years. It has enough hydrogen fuel to continue shining for another 5 billion years or so. Then it will expand into a red giant, eventually shedding its outer layers and leaving behind a slowly cooling white dwarf. The sun's total lifetime from birth to final fade will be about 10 billion years. That seems like a long time, but it's nothing compared to what's coming. Not all stars are like the sun. Massive stars, those with 10 or 20 times the sun's mass, burn through their fuel quickly and explode as supernovae after only a few million years. They are the rock stars of the cosmos, brilliant and short-lived. But small stars, red dwarfs, with only about 10% of the sun's mass, burn their hydrogen so slowly that they can shine for trillions of years. In fact, the smallest red dwarfs have theoretical lifetimes of 10 to 20 trillion years. These dim, humble stars will be the last lights in the universe. Think about that timeline. The universe is currently 13.8 billion years old. Red dwarfs will continue shining for 10 trillion years, about 700 times the current age of the universe. We're living in the early dawn of cosmic history. The universe is young. The era of stars has barely begun. Trillions of years from now, when the last red dwarf finally exhausts its fuel and fades away, that will mark the end of the stelliferous era, the age when stars illuminate the cosmos. But let's trace this timeline in more detail, because the story of the universe's far future is both fascinating and sobering. We're currently in what cosmologists call the stelliferous era. Stars are forming, shining, dying, and enriching the interstellar medium with heavy elements that form new generations of stars and planets. This era began a few 100 million years after the Big Bang, when the first stars ignited. It will last about 100 trillion years until the last stars burn out. Star formation is already slowing down. The universe's peak era of star formation was about 10 billion years ago. Since then, the rate has been declining as galaxies exhaust their supplies of cold gas. In another trillion years, star formation in most galaxies will have essentially stopped. The Milky Way will have merged with Andromeda, by then forming a giant elliptical galaxy that astronomers whimsically call Milkomeda. This galaxy will contain trillions of stars, but no new ones will be forming. The available hydrogen gas will have been used up or dispersed. As the trillions of years pass, stars will continue to die. Massive stars will have long since exploded as supernovae. Medium stars like the sun will have become white dwarfs. And gradually, even the longest-lived red dwarfs will sputter out. By 100 trillion years from now, the last ordinary star will have exhausted its nuclear fuel. The sky will go dark. The stelliferous era will end. What remains? The universe will enter what's called the degenerate era, dominated by stellar remnants, white dwarfs, neutron stars, and black holes. These objects don't shine by fusion like stars do. White dwarfs are incredibly dense balls of carbon and oxygen about the size of Earth. but containing the mass of the sun. They glow only by radiating away their residual heat. Over trillions upon trillions of years, they cool and dim, eventually becoming black dwarfs, cold and dark and invisible. Neutron stars are even denser. The collapsed cores of massive stars containing 1 to 2 solar masses compressed into a sphere only about 20 kilometers across. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. These objects are so strange, so extreme, that they challenge our understanding of physics. They rotate rapidly, sometimes hundreds of times per second, and have magnetic fields trillions of times stronger than Earth's. But they too will eventually cool and fade, losing energy through radiation, and slowly spinning down over cosmic timescales. And then there are black holes, the ultimate endpoint of stellar evolution for the most massive stars. Black holes are regions of space-time where gravity is so intense that not even light can escape. They are defined by their event horizons, the boundary beyond which nothing can return. Inside the event horizon, space-time itself is falling toward the singularity faster than light can resist. Black holes seem eternal, immune to time and change. But in 1974, Stephen Hawking discovered something astonishing. Black holes aren't truly black. They emit radiation. Hawking radiation arises from quantum effects near the event horizon. Virtual particle pairs those temporary fluctuations in the quantum vacuum occasionally appear right at the horizon. One particle falls into the black hole while the other escapes. To an outside observer, it looks like the black hole is emitting particles. This radiation carries away energy, which means the black hole is slowly losing mass, evaporating. The process is incredibly slow. A black hole with the mass of the sun would take about 10 to the power of 67 years to evaporate completely. That's a 1 followed by 67 zeros, a time scale almost beyond imagination. Supermassive black holes, like the one at the center of the Milky Way, with a mass of about 4 million suns, will take even longer. The evaporation time scales with the cube of the mass, so a supermassive black hole with 1 billion solar masses would take about 10 to the power of 100 years to evaporate. This is a Google years 10 to the power of 100 a number, so large it dwarfs all previous time scales we've discussed. For comparison, there have only been about 10 to the power of 17 seconds since the Big Bang. A Google is 10 to the power of 100. The ratio between a Google and the current age of the universe is greater than the ratio between the current age of the universe and 1 second. But even black holes will eventually evaporate. In the unimaginably distant future, after 10 to the power of 100 years or more, the last supermassive black hole will disappear in a final burst of Hawking radiation. And then, what the universe will enter its final era, what physicist Freeman Dyson called the dark era. No stars, no black holes, nothing but a thin soup of elementary particles and photons, all receding from each other due to the eternal expansion driven by dark energy. The temperature of the universe will asymptotically approach absolute zero, never quite reaching it, but getting arbitrarily close. The cosmic microwave background radiation, currently at about 2.7 Kelvin, will have been stretched by expansion to wavelengths of kilometers or more, with the temperature infinitesimally above absolute zero. Entropy will have reached its maximum. No energy gradients will remain. No work can be done. No information can be processed. The universe will have reached thermodynamic equilibrium, the heat death that physicists predicted more than a century ago. This is the big freeze scenario, the most likely fate of our universe if dark energy remains constant. It's a future of infinite expansion, infinite time, infinite cold, and infinite emptiness. Nothing happens. Nothing can happen. The universe doesn't end. It just continues forever in a state of maximum entropy, a cosmic graveyard stretching into eternity. Now, you might be wondering, what about proton decay? Protons, the particles that make up atomic nuclei, are incredibly stable. We've never observed a proton decaying. But some theories in particle physics predict that protons are not truly stable, that they decay with an extremely long half-life of perhaps 10 to the power of 36 years. If this is true, then even before black holes evaporate, all ordinary matter will have decayed into radiation and lighter particles. White dwarfs and neutron stars would gradually dissolve their protons, decaying one by one until nothing solid remained. The experimental evidence for proton decay is ambiguous. Large detectors have been built to catch the signature of a decaying proton, but none has been observed yet. This places a lower limit on the proton lifetime of at least 10 to the power of 34 years, but doesn't tell us if protons eventually decay or are truly stable forever. If protons are stable, then white dwarfs and neutron stars could persist even after all black holes have evaporated cold, dark remnants in an empty universe. If protons decay, then eventually even these remnants will dissolve into radiation. Let's pause and really think about these timescales because they're so vast that our minds can barely grasp them. The universe is currently 13.8 billion years old. Written in scientific notation, that's about 1.4 times 10 to the power of 10 years. The last stars will burn out in about 10 to the power of 14 years, 10,000 times the current age. Proton decay. If it occurs on timescales of 10 to the power of 36 years, about a trillion times longer than even the stelliferous era. Black hole evaporation takes 10 to the power of 100 years, or more incomprehensibly longer still. To put this in perspective, imagine the entire current age of the universe from the Big Bang to now represented as a single second. On this scale, the end of the stelliferous era would occur about 3 hours from now. Proton decay would happen about 80 million years from now. And the evaporation of supermassive black holes would occur about 10 to the power of 80 years from now, a time scale so vast that it makes the previous scales look like nothing. We are living in the first instant of cosmic history, a fleeting moment when the universe is young and full of light and energy. There's something profoundly melancholic about this timeline. Everything ends. Every star eventually burns out. Every planet eventually freezes or falls into a black hole. Every black hole eventually evaporates. Even time itself loses meaning when nothing changes when the universe reaches maximum entropy and no events occur. The cosmos, having blazed into existence in a moment of infinite energy, will fade into infinite cold and darkness. But here's something to consider. We are here now in this brief cosmic moment, when stars still shine, when planets orbit them, when life can exist and consciousness can arise to contemplate the universe itself. Out of all the infinite future that lies ahead, out of all those Googles of years of darkness and silence, we exist in this tiny window when the universe is interesting, when complexity and structure and life are possible. We are the universe's way of knowing itself, and we exist only because we live in this special era. Does this make our existence meaningful or meaningless? Some find these timescales depressing proof that nothing matters because everything ends. But I think there's another way to look at it. The fact that the universe won't always support life, that this era of stars and planets is temporary, makes our existence precious. We're not guaranteed. We're not eternal. We're a brief flowering of complexity in a cosmos trending towards simplicity. And that makes every moment, every experience, every connection we have with each other infinitely valuable. Think about the stars you can see in the night sky. They're temporary. Someday they'll be gone, all of them, every last one. And if anyone or anything exists in that far future trillions of years from now, they won't have stars. They won't have the beauty of a night sky full of light. They won't have planets or oceans or sunsets. They'll exist in darkness if they can't exist at all. We have something they'll never have. We have stars. We have light. We have this moment. There's a famous thought experiment in philosophy called Boltzmann brains. Given infinite time and quantum fluctuations, it's possible that random fluctuations could spontaneously create a conscious observer, a brain complete with false memories, existing for a brief moment before dissolving back into chaos. In an infinitely old universe near heat, death such Boltzmann brains might be the only form of consciousness flickering into existence and vanishing, experiencing nothing real connected to nothing. The physicist Sean Carroll has argued that we should structure our cosmology to avoid this strange conclusion, but it's a reminder of how weird the far future might be. As you lie here in the darkness, breathing slowly, feeling sleep approaching, remember this. You are made of atoms forged in stars that died billions of years ago. You exist in a universe that's 13.8 billion years old, in a galaxy that will merge with another galaxy in a few billion years, orbiting a star that will die in 5 billion years. You live in the brief window when the universe is full of light and warmth and possibility. Trillions of years from now, when the last star has faded and the universe has gone cold and dark, there will be no one to remember that stars ever existed, that planets ever formed, that life ever arose. But we're here now. We see the stars. We understand at least partially what they are, and where they came from, and where it's all going. And in this fleeting cosmic moment, that understanding connects us to something vast and ancient and profound. We are the universe looking back at itself, aware of its own deep history and far future, marveling at the fact that any of this exists at all. That awareness, that capacity for wonder, might be the most remarkable thing the universe has ever produced. And it's here now in you as you drift towards sleep under stars that won't shine forever in a universe that's slowly expanding towards silence. Every night when you close your eyes, when you settle into bed and let the day's worries drift away, something extraordinary is happening all around you. Space itself is expanding. The fabric of reality is stretching, growing, creating new distance between galaxies at a rate of 67,000 kilometers every second for every 3.26 million light years of separation. Right now, as you breathe in and out, as your heart beats steadily in the darkness, the universe is getting bigger. Distant galaxies are receding, carried away by the expansion of space. And yet, here you are safe and stable, held together by forces far stronger than cosmic expansion, living in a brief cosmic moment when stars still shine and planets still orbit, and life can exist to contemplate it all. If this journey through cosmic expansion has moved you, if you found wonder in these mysteries, give this video one final like, and subscribe so you can join us for the next cosmic story, where science meets sleep and the universe reveals its deepest secrets. We've traveled far together through this story of expansion. We began with Einstein lying awake in 1917, troubled by equations that insisted the universe couldn't be static. We watched as Hubble discovered that galaxies are receding, that the cosmos is growing. We explored what space actually is, this strange substrate of reality that can stretch and curve and ripple. We learned why you're not expanding, even though space is why gravity and electromagnetic forces hold you together, despite the universe pulling apart around you. We faced the paradox of faster-than-light recession and understood how it's possible without violating relativity. We encountered dark energy, that mysterious force accelerating everything apart. And we glimpsed the far future when the last stars will fade and the universe will go dark forever. But what does all of this mean for you, right here, right now? As you lie in bed listening to this story, what connection is there between cosmic expansion and your life, your experiences, your moment-to-moment existence? I think the connection is profound, though, perhaps not in the way you might expect. Let's return to a simple fact. Gravity holds you together. The electromagnetic force holds your atoms together. These forces are local, immediate, powerful. They create islands of stability in an expanding sea. Your body, the Earth, the solar system, our galaxy, even our local group of galaxies, all of these are gravitationally bound structures that don't participate in cosmic expansion. We are, in a very real sense, exempt from the universe's largest scale dynamics. The expansion happens around us between galaxy clusters, but not within our cosmic neighborhood. This is actually quite beautiful when you think about it. The universe has organized itself into a hierarchy of scales. At the smallest scales, quantum mechanics governs. Atoms are held together by electromagnetic forces billions of times stronger than the tug of cosmic expansion. At planetary scales, gravity creates stable orbits. The Earth will continue circling the Sun for billions of years, completely unaffected by the expansion of space. At galactic scales, the combined gravity of stars and dark matter holds everything together despite the universe trying to pull it apart. Only at the largest scales, hundreds of millions of light years and beyond, does expansion win. Galaxy clusters separate. Cosmic voids grow larger. The universe as a whole stretches and grows. But within the voids, within the expanding space, there are these islands, these bound structures where complexity can exist, where stars can form, where planets can orbit, where life can arise and consciousness can emerge to ask questions about where it all came from and where it's all going. You are one of these islands. You're a complex, organized structure in a universe trending towards simplicity. The second law of thermodynamics tells us that entropy always increases, that disorder always grows. And yet, here you are, highly ordered, highly complex, made of trillions of cells working in coordinated harmony. How is this possible? Because you're not a closed system. You take in energy from the sun through the food you eat and the air you breathe, and you use that energy to maintain your structure, to fight against entropy, to stay organized. You're a temporary local decrease in entropy, possible only because the sun is increasing its entropy much faster by fusing hydrogen into helium. The sun itself is a temporary structure burning through its fuel, converting mass to energy, increasing the universe's total entropy. In 5 billion years, it will swell into a red giant and eventually fade into a white dwarf. But for now, for this brief cosmic moment, it shines steadily, providing the energy that makes life on Earth possible. We exist in the sun's stable phase in the era when stars illuminate the cosmos, in the early morning of cosmic history, when complexity is still possible. Think about what a privilege this is. Of all the vast stretches of cosmic time, of all the Googles of years that lie ahead in the dark future, we exist now in this brief window of light and warmth. The universe could have evolved in countless ways. The fundamental constants of physics could have been different, making stars impossible, or life impossible, or consciousness impossible. But somehow, the universe is arranged exactly right for us to exist. The expansion rate is fast enough that the universe doesn't collapse immediately, but slow enough that structures can form. Dark energy is strong enough to drive acceleration, but not so strong that it tears everything apart. The strength of gravity is precisely calibrated to allow star formation without causing immediate collapse. Some physicists call this the fine-tuning problem. Why is the universe so precisely balanced? Some invoke the anthropic principle the universe must be this way, because if it weren't, we wouldn't be here to observe it. Others suggest we might live in a multiverse, an infinite collection of universes with different laws of physics, and we naturally find ourselves in one of the rare universes where life is possible. Still others search for a deeper principle, some as yet undiscovered law that explains why the constants have the values they do. But regardless of why the universe is the way it is, the fact remains we're here. We exist. We're conscious. We can look up at the stars and understand what they are. We can measure cosmic expansion and trace it back to the Big Bang. We can predict the far future and see how it all ends. This capacity for understanding, this ability to comprehend our place in the cosmos, is perhaps the most remarkable thing the universe has produced. Carl Sagan famously said, "We are a way for the cosmos to know itself." And he was right. The atoms in your body were forged in stars that died before the sun was born. You are literally made of stardust. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it came from stars. And now those atoms are arranged in such a way that they can think, can feel, can wonder about their own cosmic origins. The universe has spent 13.8 billion years evolving from a hot, dense state into its current form. And part of that evolution includes you thinking about the universe, thinking about itself. There's something almost mystical about this, though. It's grounded in pure physics. Consciousness is an emergent property of matter, something that arises when atoms are arranged in sufficiently complex patterns. Your brain contains about 86 billion neurons, each connected to thousands of others, creating a network of unimaginable complexity. Somehow, from this network of electrical and chemical signals, awareness emerges. You experience colors, sounds, emotions, thoughts. You have a sense of self, a feeling of being a unified entity despite being made of trillions of separate cells. And in this moment, as you lie here listening, that awareness is contemplating the expanding universe. You're thinking about space stretching, about galaxies receding, about the far future when stars will fade. Your consciousness, this temporary pattern of neural activity, is engaging with cosmic questions that span billions of years and billions of light years. You're connecting the intimate scale of your immediate experience with the vast scale of cosmic evolution. That's extraordinary. That's profound. That's the universe experiencing itself. Now, as sleep begins to find you, as your thoughts start to dissolve and drift, let yourself feel your place in this expanding cosmos. You're lying on a planet that's spinning at 1,600 kilometers per hour at the equator. That planet is orbiting a star at 30 kilometers per second. That star is moving through the galaxy at 220 kilometers per second. The galaxy itself is moving through space at about 600 kilometers per second. And space itself is expanding, carrying distant galaxies away at speeds that increase with distance, reaching and exceeding the speed of light for the most distant objects. But you don't feel any of this motion. You feel still. You feel at rest. Because all of these motions are relative. There's no absolute reference frame, no cosmic background against which motion is measured. You're at rest in your own reference frame, and that's just as valid as any other. The universe doesn't have a center or an edge. Every point is equally valid. You are in a very real sense at the center of your own observable universe, with everything expanding away from you in all directions. This is not a metaphor or a spiritual teaching. It's literal physics. The observable universe is defined by the sphere of space from which light has had time to reach you since the Big Bang. That sphere is centered on you because you're the observer. Every conscious being in the universe, whether on Earth or on some planet orbiting a distant star in a distant galaxy, is at the center of their own observable universe. There are as many observable universes as there are observers, all overlapping but not identical, all expanding, all centered on their respective observers. Does this mean you're special? Yes and no. You're not special in the sense that the universe was designed for you or revolves around you. The cosmos is vast and ancient and largely indifferent to human concerns. But you are special in the sense that you exist at all, that you're conscious, that you can experience and understand. In a universe that will eventually fade into maximum entropy and eternal darkness, the fact that complexity and consciousness exist right now is genuinely remarkable. You're a temporary flowering of organization in a cosmos trending toward disorder. That's worth celebrating. And here's something else worth celebrating. You're not alone. Right now, there are about 8 billion other humans on Earth, all experiencing their own lives, all contemplating their own questions. There might be billions or trillions of planets in the Milky Way alone. Some of them likely harbor life. Some of that life might be intelligent, might be looking up at their own night sky, might be asking the same questions we ask. We might not be alone in the universe. We might be part of a vast community of conscious beings scattered across galaxies, all trying to understand the same cosmic mysteries. We haven't found evidence of other intelligent life yet. The universe seems strangely quiet, what physicist Enrico Fermi called the Fermi paradox. Where is everybody? If the universe is so vast and so old, why haven't we detected signals from other civilizations? Maybe intelligence is rare. Maybe civilizations destroy themselves before they can spread across the stars. Maybe the distances are simply too vast for communication. Or maybe we're the earliest, the universe's first attempt at self-awareness. We don't know. But the question itself is profound, and someday we might find the answer. For now, though, we have this moment. We have the stars above us still shining after billions of years. We have the earth beneath us, a rare oasis of life in the cosmic desert. We have each other, fellow travelers on this spinning rock, all experiencing the mystery of existence together. And we have the knowledge that we've gained the understanding, we've achieved the questions we've learned to ask. We know the universe is expanding. We know it had a beginning and will have an end. We know we're made of stardust, that we're temporary patterns of matter and energy, that we're the universe's way of knowing itself. What should we do with this knowledge? How should we live? Knowing what we know about cosmic expansion and the far future and the ultimate fate of everything. I think the answer is simple. We should live fully, love, deeply seek understanding, create beauty, care for each other, and marvel at the extraordinary fact that any of this exists at all. The universe will eventually go dark. Entropy will win. Everything will fade, but not yet. Not for trillions of years. Right now, in this cosmic instant, we're alive. We're conscious. We're here. And that's enough. As sleep takes you now, as your breathing slows and your thoughts dissolve, let yourself rest in the knowledge of your place in the cosmos. You're a small part of an expanding universe held together by forces stronger than expansion itself, living in a brief era when stars still shine and life is possible. You're made of atoms forged in stars, arranged in patterns complex enough to wonder about their own origins. You're the universe experiencing itself conscious and aware, and marveling at the mystery of existence. The space around you is expanding right now, stretching at 67,000 kilometers per second, per megaparsec, carrying distant galaxies away into the dark. But gravity holds you to the Earth. Electromagnetic forces hold your atoms together. You're safe, stable, an island of organization in an expanding sea. And in this moment, in this quiet darkness, you can rest, knowing that you're part of something vast and ancient and beautiful, something that began 8 billion years ago, and will continue for googles of years into the future. You're a brief note in an eternal cosmic symphony, and your note matters because it's the only note you'll ever play. Sleep well, friend. Dream of stars and galaxies and the expanding universe. Dream of space stretching and light traveling and time flowing forward toward an inevitable but distant end. And when you wake, remember what you've learned, that you're made of stardust, that you're the cosmos, knowing itself that you exist in a brief window of cosmic time when everything is still possible. We are so fortunate to be here now, in this moment of light between infinite darkness. Cherish it, live it fully, and keep looking up at those stars, those distant suns receding into the expanding dark, still shining, still beautiful, still calling us to wonder and to understand. Thank you for joining me on this journey through the expanding cosmos. Thank you for your curiosity, your patience, your willingness to contemplate these vast questions as you drift towards sleep. I hope you found something here worth thinking about, something that connects you to the universe in a new way. If you enjoyed this exploration, there are many more cosmic stories waiting to be told, many more mysteries to unravel, many more questions to ask. Subscribe so you don't miss them. Each one is a window into the wonder of existence, a chance to see the universe from a new angle, to understand something profound about reality and our place in it. Until next time, sleep well under these expanding stars. The universe is vast and strange and beautiful, and you're a part of it all. Good night.